Hello everyone and welcome back to our final workshop of today, Beach Blitz Day 2. Before we begin, I would just like to introduce our next workshop presenter, Pauline. She's our very own Beach Blitz director, and she's also an OCRA board member and currently working at Virgin Hyperloop as a process development engineer. She's going to be talking about how the nuts and bolts of manufacturing work and how to optimize your tools and efficiently use them to your advantage. Pauline's honestly one of a kind and is super passionate about her work with manufacturing. So without further ado, take it away.
Thanks, Hester. That's very sweet. All right, gotta do double duty here. Let's share my screen. Um, all right. Hester, can you see that?
Yes, I can.
All right. Well, hello, everyone. Thank you so much for another day of Beach Blitz workshops. I'm super excited to teach today. I think my internet just cut out. No, it didn't. Okay. Super excited to teach today. So what I'll be going over today is setting up your manufacturing for success. And this is a very passionate, I have the twitch in the whatever, setting up your manufacturing for success. I'm very passionate about this topic and I'm really excited to teach it to you guys. So a little bit about me that Hester alluded to. I am an OCRA board member. OCRA is the Orange County Robotics Alliance. I'm the co-founder and event director of Beach Blitz. This is our 5th installment, so I'm super excited about it. I'm a manufacturing engineer at Virgin Hyperloop. I have a bachelor's degree in manufacturing engineering as well from Cal Poly Pomona. I'm a TEDx speaker. I've done a TED talk about human curiosity and becoming an interplanetary species. And a little bit about me and FRC. I've had quite a journey. I started out in robotics as a high school freshman and 589 Falcon Robotics. I was a student. I was mechanical outreach and manufacturing for those 4 years. And the next step, once I got to college, I started mentoring 3476 Code Orange for 4 years as well. I did pit leader and I was mechanical manufacturing and outreach as well. After that, I did a year with 2659, the Robo Warriors. I also did mechanical design and manufacturing. There's a theme. Now I serve as a volunteer all over the place. I do field supervising and help run events like this. Yeah. So really, what is this workshop about? And so when I sat down to create this workshop, I wanted to do something a little bit different than what you guys are used to seeing. I think there's a lot of resources specifically about how to make parts and how to do these kind of things. But what we're really doing is, what does manufacturing success look like in the workplace and how can you transfer that to an application within your robotics team? And so like those images say, the left image is kind of how it is in the workplace, how it is in the big old world. And to the right is how you can use those tools to climb up that ladder of success and use some of that in order to make your team better for manufacturing. All right. So what are manufacturing engineers' goals? The first up, the main goal is you're turning ideas into reality. Really what that is you're making parts correctly and consistently. You're putting assemblies together efficiently, making sure all parts come within a timely manner, meaning don't go over your time constraint. Working with designers to create well-integrated systems, or your CADRs as FRC teams like to call it, ensuring the best quality whenever possible. And then the main 3 reductions are reducing time, cost, and waste. And we'll get into all of these goals and how we achieve them in the real world and how we can achieve them in an FRC sense. But the overall objective and the overarching theme for manufacturing engineering and manufacturing success is eliminating inefficient use of time and waste to make better parts. So there's a little thinking hat. All right. Manufacturing engineers achieve their objectives using what I like to call their tool belt. It's their tool belt of programs, machines, and ideologies. And really what it is, as cheesy as it sounds, is as an engineer, as you're sitting here trying to design something and make something, whatever kind of engineer you are, you have all these different things that are getting crammed into your brain. This is why some people go to school for engineering. You guys learn it in the workplace or in the shop for FRC. You learn how to use CAD, you learn how to do this. Everything like that, you kind of all fall into a tool belt that you could use. Everything you learn gets stored in the back of your head as something you could use in the future. So for a manufacturing engineer, we kind of have 3 main ones, which is programs, machines, and ideologies. So the first tool in our toolkit, of course, is tools, as obvious as that sounds. Tools are what instantly come to mind when you think of manufacturing and manufacturing engineering. I think when I was a high school student, I thought it was the only part of manufacturing, and we'll get into some of the other ones. But tools and processes need to be extremely precise and specific to their purpose. You need to know which tool is the best for a certain application. And what that means is you're not using a plier to hammer down a bolt. That doesn't make any sense. You need to use the right tool for the job, because if you do use the right tool for the job, you actually make better products. You're doing it faster. You're not ruining your tools. And I'll be the first one to tell you, if it is a time crunch, we're in a limbs and finals on Einstein and I need to put something in and I don't have the tool next to me, I'll grab a plier every now and then and pummel something with it. But in reality, if you use the best tool for the job, it'll always get accomplished better. It will be better and it'll be more repeatable. When you do that, when you find the right tool and the right process specifically for the job, you actually take the guesswork out of putting something together or making something. If you know which tool, like I need to use an angle grinder to cut this specific thing rather than a chop saw, you're making that part better. You're making that part within the tolerances that you've wanted to achieve. So there's a lot of tools that a manufacturing engineer can use. I would spend maybe a week straight talking about all the different tools available in manufacturing, but we don't have that kind of time, nor do I want to talk about that for that long. But some of the tools that I think most FRC teams are familiar with, or they're right on the cusp of being familiar with it, are hand tools, power tools, stuff like mills and lathes, CNC machines, or computer numerical control machines, 3D printers, laser cutters, water jets, welders and brazers, tooling and jigs, which I know are not really familiar with in FRC, but we'll get into it. And then plastics injection molding. And again, like I said, much, much more. If you're really interested in all the cool types of machining and manufacturing out there, feel free to send me a Discord message. I could talk about all the cool types of machines I've seen in my day for quite a long time. So if you're interested in stuff more like that, feel free to message me on Discord. And so we're going to go through a little bit of the different kinds of tools familiar with the workplace and with FRC. The first up seems pretty trivial, but it is hand tools. Hand tools are the most widely used tools out there. A hammer, a screwdriver, anything like that. They're the most widely used. You can find them in every single shop and in any FRC team and any company all around the world. And the reason that is, it's because it's the easiest to learn and get trained on. Really, it's not a lot of training, not a lot of risk. They're the cheapest to buy. Considering, Harbor Freight's out there, Home Depot, but there's also larger suppliers too. They're easy to repair. And most importantly, they can be used for so many different applications. The versatility in hand tools is really insane. I could use a hammer for 100 things, but when you get into more specific tooling, it might do one thing really, really well, but you can't do, a bunch of things really well like you could with some hand tools. The problem with hand tools are they're not really that accurate. If I want to torque something down and put a bolt in a certain way, you're only going to be able to have a little bit of control with that. You're not going to be able to really know how tight it is, how loose it is. If you're using a hacksaw, you're not going to really know if you're being straight with your cut because you can go all over the place, stuff like that. So that's why we move beyond hand tools when we get into some deeper manufacturing. Next up, we have power tools, which is my favorite category in the lower level. Power tools are similar to hand tools where they don't take actually a large amount of training. And I like power tools a lot because I think it's the first step in FRC where you really get to play with your hands a little bit more. It's not just when, your parent told you to pass you a screwdriver. This is a little bit more involved. You get to, work with your hands a little bit more, see metal fly all over the place. And I think that's a little bit more fun. But regardless, power tools do require a bit more safety training and certification. The good thing about power tools specifically is they are more specific in their applications. Like I mentioned earlier, a chop saw cuts. It cuts straight lines, it cuts angled lines. That is the purpose of a chop saw. They're more specific. So because they are more specific, they have a higher level of accuracy. But because of that, they have less repeatability than hand tools and less versatility than hand tools. Right, next are mills and lathes. So in the context of the workplace, mills and lathes are actually on the lower intermediate tool that is used. But in the context of FRC, I would consider a hand mill and lathe intermediate to advanced. For sure, mills and lathes require certification, and they're much more accurate than hand or power tools. And I know at first glance, a mill kind of just looks like a drill press. And It basically is, but it's a drill press that you could move in X, Y, and Z directions, which is extremely useful when you're trying to make a part. But really what makes it super accurate are digital readouts, which is the top right image with those 3 green numbers. And there are actually dial indicators on some mills that do not have digital readouts, which basically means you're counting rotations and you know how much you've moved because of that. And the reason that we like mills and lathes, especially in FRC and especially in the workplace, is it's easy to be accurate. You can't be super, super accurate. Obviously, there's some, human movement involved, but it's so easy to get into an accuracy level that you're comfortable in, especially when you're making FRC parts, especially when you're making something that doesn't really need that high of a tolerance or anything like that. Another reason why mills and lathes are so accurate, it's you're calibrating the machine before you actually put anything on it. And so to the right, you'll see a dial indicator. Essentially what you're doing is you're trying to find the zeros of the machine in order for you to just really easily plug parts in and be ordered to manufacture them efficiently and easily. All right, next up are some CNC machines, computer numerical control machines. These are one of the most accurate standard tools. Obviously, there are much more accurate tools out there, but I do think a majority of workplaces have CNC machines. I think CNC machines are growing in FRC as well. And how these work is essentially like your mill and lathe. We'll talk about CNC mills and lathes. There's a whole other category of CNC water jets and CNC laser cutters and stuff like that. But for the purposes of this, we'll talk about CNC mills and lathes. Why these are so accurate is users are actually creating a program that auto measures and uses a coordinate system in order to create parts. And what that means is I can throw a part in there. My CNC machine, through the code that I write, which I'll get into in a second, will be able to zero along one of the edges of my part. And then from the program that I asked it to do, it'll know exactly where it needs to go, how deep it needs to go. There is no hand movement. It's all accurate and consistent, which you don't get with mills and lathes. On a mill and lathe, you're kind of controlling the pressure when you put that drill bit down. But on a CNC machine, it is all consistent because it's the machine that controls it. In order to make those programs, there's a couple different things you can do. If you just want to write a short program, you could actually write it on the machine in something called G-code. There's a lot of resources on that. When I learned how to use a CNC machine, my professor was adamant that I had to write in G-code first. So you have to be like part, cycle on, turn this off, and you write that all down. But once you start making parts that are a little bit more involved, you definitely want to use a CAM software. CAM is computer aided manufacturing. And what that is, it's basically you take your part that you've CAD'd up and you want to figure out the tool path that you want your CNC machine to cut. You want to say, hey, I want to measure here. I need these 4 holes. I want it to go from this hole to this hole and then do this cut. And so it's really common used in the workplace, especially Mastercam. Mastercam is most widely used in the workplace, but I did want to tell you about more. Some of the other popular ones are HSM Works, which is owned by Autodesk, and Fusion 360, which is my highest recommendation for FRC teams. It's free for all students. You don't even need an educational email. You just need to say you're from a school. You can import easily parts from SolidWorks, Onshape, Inventor, Creo even. And that's the one I would recommend the most. Mastercam and HSM Works are really well integrated with their specific software, but Fusion 360 is free, and it's, to be honest, the easiest one I've ever had to learn because it's really intuitive and they have the most training available. Last up for CNC machines, I wanted to recommend Haas Automation. Haas Automation is a CNC company. They make CNC machines. Actually, I had an internship there a couple years ago. They have educational discounts and the absolute best repair policy there is for CNC machines. They have loads of resources available, unlike most of the CNC companies you'll see, because they specifically are geared towards people who are new in CNC machining. And so Haas actually offers a bunch of training videos on their website. They have Haas tips of the day, as well as they have worksheets on their website if you want to, teach your other students or other students as well, kind of you want to teach them on paper before they might crash a machine. They have really, really good resources on that, and I couldn't recommend it more. And so the pictures to the right, that's me with a CNC machine. The day code orange got the first one. To the top is actually a part that I decided to CNC machine to show how accurate CNCs can be. And so this is actually only half of the assembly. The other half is, kind of like the convex of that, like that hole is then, deep and all these holes up here deep as well. So they actually fit into each other. And what I wanted to see with the CNC machine is how accurate can this be? And of course, this is a little foam board. It's not metal, it's not wood, it's not something that holds its shape as accurately as some of those other materials. But when these fit together, they fit together well. And that's something you can only really achieve on a CNC machine if you're machining stuff really that close. When you get into a mill and lathe, you're gonna have much more wiggle room because a person is applying that pressure. And then to the bottom, that's a computer graphic. That's actually what the panel looks like on a Haas mill, a Haas mini mill. And so before you run your part, you already made your cam, you plug it into the CNC machine. I will always recommend to run it dry, meaning don't actually run like the spindles and the parts. You're just running the code and a picture, and that green line is showing where your tool path is. You always want to do that first because your machine will tell you if there's any errors, if there's any collisions that you might have not seen in your software. And you just want to look at it before. I have crashed CNC machines in my day, and you don't want to do that. So, yep. All right, next up, which I think most of us are familiar with, are 3D printers. And 3D printers are really dependent on which printer. The level of accuracy can vary from, not very good to extremely good. And 3D printers are the absolute most versatile tool in a manufacturing engineer's toolkit, but one of the least accurate for common models. So that picture at the bottom is an Ender 3, which is a common model. It's under $200. I used to have one in my old apartment that I would play with all the time. It's really great for creating what you need, but it's not going to be as accurate as some stuff that you might need for your manufacturing team. If you don't need accuracy, then stuff like that is good. That goes back to the idea of finding the tool for the purpose, and that's really how you make the best manufacturing. Some other things on there are an Airwolf, which I know has a really great educational discount. That's the top image. You can print different kinds of plastics in there, ABS, PLA, as well as I believe a wax filament. And then my favorite 3D printer of all time is a Markforged. Markforged is really great. They make such accurate parts. To be honest, if I looked at it from a distance, I would think it's a metal manufactured part. You can actually interweave it with some really strong material. So they're very expensive, but they're awesome 3D printers if you're ever wanting to know anything about them. With a 3D printer, kind of like with CNC machining, you kind of need to create software of how you want your machine to actually cut things up. And so the slicing software is what it's called. I always recommend Cura. It works with nearly every 3D printer, unless there's a 3D printer that will only let you use one. Cura is the most accurate. It is free, and I would highly recommend it if people did not know what Cura slicing software was. And the most important tool in a manufacturing engineer's tool belt are tooling, fixtures, and jigs. And the reason I wanted to bring this up specifically is I feel like when I was a student, I had no idea what tooling, fixtures, and jigs were. I really didn't know what it was until I had my first internship in college. And it is honestly the best way you can make parts consistently and good and the best possible. And why it is, it's because it's customized and it's for a specific application. You only use this tooling or this fixture for one thing. So if your team, for example, needs to create like 40 L brackets that all have the same hole pattern, they all have tool holes in the bottom and tool holes on the side, it's going to get really annoying if you have to keep putting that L bracket in, measuring it up and milling, and then take that L bracket out, do the whole process over again. But if you could create tooling that kind of holds all those L brackets in the same place, put them all in the line. So all you have to do is you put it in, measure once at the beginning, drill your holes in. And then once you're done with that, all you have to do is take those parts out and put new parts in. You don't have to remeasure because that piece of tooling, that fixture is still there. And I know that sounds a little confusing. So those pictures kind of help with that. So that top image is kind of like what I mentioned. Instead of L brackets, it's these little squares that are getting holes machined into them. And those little squares are held on a large piece of tooling, is that lighter metal color. They're bolted into it. And so every part that is ever machined on this is exactly in the same place. That piece of tooling doesn't necessarily get removed from the CNC machine, or from the machine. You only have to line it up once. And so now you could drill these holes accurately every time. You could do multiple things at once with that as well. So if you have a common part that's used so often for your FRC team, tooling is a way to do it. If you know you're going to do a bunch of gussets, or you're going to make a bunch of L brackets or anything like that, this is the way to do it, and so that they're all the same. And so when you start needing to use it, you're like, oh, those holes are, a little bit off to the side, and these holes are a little bit off to the side. When you have tooling, it prevents all of that. Another good example is this CAD image I made to the bottom. And so basically what this is a shaft. And essentially I wanted to be able to drill in these 2 holes at the top of the latter part of the shaft. And because it's circular, it's already been laid down, you can't actually hold that part very well in a mill unless you have something like called soft jaws. And so what I ended up doing is I wanted to create tooling. And so I ended up making this brown little tool, and it holds the part down and it bolts down into the holes that I already created. And from that, I can actually now put it in my mill because now there are flat surfaces. And so sometimes tooling comes out of necessity like that, where I can't actually hold the part. And sometimes tooling comes out of, I want to create a lot of these really accurately. And that's where tooling comes in as well. Jigs are similar. Jigs are basically the same thing. They're all kind of the same thing. All right, next up are processes. And so I wanted to talk about processes a little bit briefly, but I wanted to talk about them because they're often mixed up with tools. And the difference is, for example, a tool is a mill. The tool you are using is a mill, but the process is milling. And I know that sounds trivial, but the reason it's not is because at the end of the day, you can actually use multiple tools to make a new process. And so another easy one is, a welder is the tool, but you're doing the act of welding. But you could do different things with a welder. And I'll get into it. That picture to the right is what's taught at Cal Poly Pomona's manufacturing class. They basically have a bunch of machines and processes, and you make a truck in the back. And that's what I had when I was a student. Yeah. So I'll use an example for a process. It's my favorite example personally. So the example I like to use is metal casting. Metal casting is essentially a process where you melt molten metal and pour it into a mold cavity. And after you cool, you actually have the part. And I know that sounds confusing, so I tried to lay it out here. So that bottom image, that bottom schematic is kind of how green sand casting, which is a type of metal casting. There's a bunch of different types, but this is the most common and the cheapest. You basically have 2 sides of a mold. There's a top and a bottom. It's called the cope and the drag. And you fill it up with sand, you press a mold into it, and then you close it up, fill the other side with sand, press it down really, really tough so it really has a nice layer of whatever you pressed inside of it. Open it back up, take that mold out, close it, and then pour molten metal into it. You have to make your own like rivers or gates and runners. So the example I have here is a Bowie knife I made for a competition. And so the far left image is the 3D print of the Bowie knife. And so our bed was a little too small, so we actually printed it in 3 separate layers. And it turned out all right to not have those lines, but that's our Bowie knife. We 3D printed it. And the next step is actually to put it in the mold cavity. And so you take those 2 sides, like I said, you fill it up, put sand, and you pound that sand down so you really get an accurate finish. And then you add these little weights on top so that it doesn't move up in the process. You add that little hole on top, a little river down to your cavity, and you pour some molten metal into it, which is step 3. That's me with the hair tie, pouring molten metal into those molds. And then once it's cooled, you get your part out of it. So that's the Bowie knife with those rivers, with that sprue, with everything, not finished at all, but that's what it looks like. If you're curious why it looks so dimply, it's because you're supposed to sift your sand so that it doesn't have any clumps, because that could show through your metal cast. I was too lazy to sift my sand, so I had no time. That's what I did. Ended up having to remake the part. Goes into the same thing of do it right the first time. But that's the process. So again, this is the process. You're using multiple tools, though. I'm using a 3D printer as a tool for my process. I'm using a hammer to pound it down as the tool, but it's not the process. The process is completely different. So number 3 in our tool belt that we were talking about are standards and training. And so standards, or SOPs, as the workplace likes to call it, are standard operating procedures. And essentially what standard operating procedures are, it's a brief step-by-step instruction that's specific to the operation that describes what's necessary to complete the task. The way I like to describe SOPs specifically is when you think of a peanut butter and jelly sandwich, it's basically, when you think about it, an SOP is just a Word doc. And so at the top of my SOP, I have, okay, the materials I need is bread, I need peanut butter, and I need jelly. And then the tools I need are, a knife, 2 knives if you're not insane, because you should not mix your peanut butter and jelly in the same jar. That drives me crazy. So those are your tools, and that's your material. And then your process is, step 1, take slice bread out. Step 2, put some peanut butter on it, step 3, et cetera, et cetera. And those steps get way more detailed in an actual, complex situation. For peanut butter and jelly, it's a little different. Beyond that, you could do things like work instructions, which is a step-by-step guide to build nearly everything. One of my favorite examples of this are literally Legos. We love Legos here. I build a lot of them. And they actually make work instructions. And what they really are is you can see the exploded view of this little Lego man with a scarf. You can see all the parts that are involved in it, what it's going to look like in the end. And then they take you through the build process. They say, all right, you're going to start off with this part, and then you're going to put this part in. You're going to turn this part around. You're going to do this and that. That's really what work instructions are. And I know it sounds, oh, it's just Lego. But when you get to, bigger engineering tasks and bigger manufacturing tasks, you really have to develop these instructions so you ensure that these parts are done correctly. And when you get into assembly mode as well, you want to make sure that you tell whoever is going to assemble it that this part needs to be placed on first, this part needs to be placed on next. Because if you don't give any instruction, and then you're left with all this time of what should I do, where should I go, what should I use? But if you define it at the beginning, you save so much time and energy, and you don't mess up a bunch of assembling work that you've already had to do. So some work instructions continued in an engineering sense. I know there's a lot on the screen. I'm not going to make you try to read it. Don't worry. But the left, these are two different pictures. The left is kind of an exploded view. This is what I would call what a design engineer might give a manufacturing engineer. And to the left, you can see that all these different parts are involved in this one part. But what you don't see is how these different parts are made. You see how they're put together, but I don't know how this housing is made. I don't know how this plunger is made. I don't know how anything is made in this. I just know that these bolts go into this cover, into this gasket, into the plunger, and into the housing. I don't know how tight these screws need to be. I don't know if I need to press down firmly or apply any grease or anything like that. That's not on there. That's stuff that work instructions do need to say. And so another example of what maybe someone would give you, a CADer in your design team or anything like that, they might develop a drawing. Obviously not as involved as this drawing. This was for a Cal Poly Pomona class, but this is a stock guide, and you'd basically get your measurements of, hey, I need this to be 0.80, I need this to be 0.61, this hole is a 1/2-inch hole, stuff like that. If you're curious, all these rectangles are things called tolerances. And tolerances in the workplace actually determine what machines you use. So if you have a tight tolerance, that means something is hard to achieve. You need to work a little harder to get it. You got to use a more precise tool. And so I'll go into one example. The parallelogram there is called flatness. And so what flatness is imagine if you're cutting a tube, a 1x1 tube. And if you cut it with a hacksaw, you can't really determine the flatness of that because you don't know if you're angled at all. You don't know if you're cutting perfectly straight. You don't know if you're missing any bumps on the road. But if you cut it with something that's a little bit more accurate, let's say you shave it off with a mill, you are able to achieve a better flatness. But now you have to use a more complex tool. It goes again to the point, you're finding the right tool and the right process for the part. It's much faster to do with the hacksaw. If I don't need to care about that straightness or that flatness at all, use the hacksaw, it's faster. But if I do need to care, it is much faster and better and accurate to use something like the mill. Okay, so work instructions. And so to make that part that I showed in that drawing, here are just two examples of some of the operations. There was over, I think, 110 different operations I made for the work instructions. But for this operation, you could see operation 40 is I'm turning this part down 0.38 OD, and then this outer part 0.20 outer diameter, and then chamfering the end. And why you do work instructions is it's super clear to see what you need to do. And I'm not saying your FRC team needs to create this for really easy parts, but if you think it's something that a person is going to have a little bit of a tough time with, or it's a more complex part that it needs to be done in a certain step, like this one actually needs to be flipped in operation 70, so it's a little bit more involved, then you want to create some type of work instruction just so it's a little bit easier for them to see. And I'd always recommend using pictures and PowerPoints. In the real world, in my job, I make so many PowerPoints of exactly what I want someone to build or manufacture. So this is what it is. If you're curious, these gray triangles on the side are where the machine is holding the tool. So this is in a lathe right now. Those gray parts is where it's being held, and that blue is kind of the cutting surface of where I'm going to kind of plunge into. All right, next up that kind of goes along with that are process maps. And so process maps are something I've integrated personally into FRC. This is an example with priming a plane. But basically what they are is you're saying this needs to be done first, this needs to be done second, third, fourth, fifth, and sixth. And so the way I like to think about it is if you're building a drive base per se, and the first step of it is to cut your metal. The second step is to drill in your bearing holes. The third step is to put in your bearing holes. Having that process laid out somewhere is really good. And you can expand it to larger processes, obviously, into the entire system. But the best part about it is that you can really lay everything out. And so in a typical process map, these shapes mean different things. You definitely don't need to know that, but like things like inspections are circles, processes are squares, stuff like that. But just having somewhere where you could lay out what needs to be done before something else will really help your manufacturers. And so now your designer or your mentor doesn't just have to constantly be sitting there being like, all right, this is the next step. This is the next step. If you have it laid out, you're able to just do it on your own, which is the goal. You want to be able to do things on your own and do them well. Last up in that category of standards are training documentation. And so these are specific to FRC. Some of the training documentation I'd recommend. The first one is 3476 Code Orange manufacturing training, some of the best that we've had. And so I really like that. It goes through basic and intermediate tools. So you could see all of that. There's a mill and lathe project in there as well. Next up is a 696 circuit breaker Haas CNC training videos. It's really great. Honestly, they showed that at my college so many times. They're really great. They show how to exactly use the Haas mill, especially the education mill, which I'm sure a lot of teams would apply for. Next, I'd recommend the Fusion 360 training. The Fusion 360 training is that CAM software for CNC machines that I talked about. I again recommend this because it's free for students, but I also recommend it because as a student, you can enroll in the free workshops they have online and actually build with them and do CAM with them. So I definitely recommend doing that. All right, tool belt number 4, all right, is organization and ideologies. And so I know, we always start off organized and then it all goes away when the time crunch hits. It's bag day in 2 weeks. We don't have parts coming in. We're just going to put this wrench over here. We're just going to throw things everywhere. And I used to, think about this all the time when I was mentoring and was doing manufacturing. I was saying, why aren't people putting things away? Why aren't people just putting things where they belong? Why aren't things where they should be? I'm looking for one hole saw. It's missing. I can't find it. And I think all of us in FRC can really relate to that. We're all kind of all over the place. But, really what I found out and I've applied is that if it's easier to be messy, people will be messy. If it's easier for me to put that wrench next to me, that means that wrench doesn't have a good place next to where it's commonly used. And it took me a really long time to kind of grasp that aspect of it's not that people are lazy or that people don't want to put things away. It's because it's easier to not put things away because they're not where they should be. And so when you make things easier to be organized and in their place, that's the key to a successful shop. Because when you're not looking for things, you perform better. When you're using the right tool for the job and you know where to find it, you perform better. You make accurate parts, you make good parts, and you assemble much quicker. And it saves you a hell of a lot of time. And so that's all talk, right? But the key ideologies of how to kind of get that organized shop is through 4 different processes that we'll go through. They're called Lean, 5S, Six Sigma, and Kanbans. That image to the right, by the way, is an example of what I mean when I say a tool has its place. And so this board has this many holes because this is how many, collets I have. This is how many things I have. And it goes in there. If it's only in that one hole, you can't put it somewhere else. I would personally go as far as labeling each of those so you know exactly where it needs to be. But see how that part is right next to your mill machine. You're not going to want to walk across your shop to find your collets. You're going to want to be right next to your machine. And so when you think about it in the FRC world, if you assemble on one table, you want your assembly tools next to that area. If you're going to assemble in this area and I want all my hex drivers right there, I want all my drill bits right there. And sometimes that means you need 2 sets of tools to do things, but that way things are not getting lost nearly as often. All right, so let's go through some of the key ideologies. So first up is lean or lean manufacturing. Lean is essentially the idea that you could take this process that's kind of all over the place and shrink it down to be a little bit more efficient. And it's a little bit different with FRC because, every year is a little different. You're making something a little differently. But there are some things that are super common that you make every year. I mean, You're going to make some of the same brackets. You're going to make some of the same things, some of the same drive bases. And having a way where you could shrink that time as much as possible, but still make really good product is how you save your time in your FRC season and make better products. I had one year where we had to remake the drive rails 6 different times. And when you really narrow down the process, because you're creating it so many times, you're able to make better product. And so the lean way of thinking is it's 5 steps. And this is how a company would do it. And I'm going to break it down how you would do it in FRC. The first step is to identify customers and specify value. And so what that means in an FRC sense is you are the customer. You get to pick what you think the value is. And so for a drive base, for example, the value in the drive base is I need it to be accurate. I need it to have the holes in the right place. That's the value I have in that specific drive rail. What is not value is I don't need it to be sanded necessarily. That's not much value. I don't need it to be powder coated. That's not much value added. It's not accomplishing the task that I set out to do. The thing that's the most important is the value is that the holes are in the right place so I could use it properly. Next up is identifying and mapping the stream. And so this is a big process in the workplace. This is a whole thing called value stream mapping that if you're interested, definitely hit me up. It's a fun, like really cool Excel sheet. But for the purposes of this, what this means is you're kind of going through your steps to make that. You're going through your step 1 is to cut your tube. Step 2, drill the holes. Step 3, deburr, stuff like that. You're going through and identifying really how long those really take, if there are any bottlenecks. A bottleneck is something that takes so long, it prevents you from doing something else. You go through that process, figure out how long it typically takes you to do it, figure out your efficiencies, you figure out stuff like that. And you take that information of just observing a process and you create flow by eliminating waste. And what waste is stuff that, necessarily doesn't need to be done. And so the biggest one in this of how people typically eliminate waste specifically is where things are, which goes back to our organizational area. If I'm cutting a part, or if let's say I'm milling a part, if I don't have that stuff readily available near me, and let's say it takes me 10 minutes to mill the 3 holes into the side of the tube for the drive base. If I don't have the things I need next to me, like, the end mill, like the collets, like the calipers, like anything like that, and I have to keep walking across the shop to get those things, your 10 minutes of cutting just went up to, 15 or 20 minutes just because you're spending time looking for things. You're spending time going across the shop. Really, your elimination of waste is when you use things consistently at the same place, you keep them at that same place and you label them nice so that they're always there. When you do that, I promise you, your parts will come out faster. I cannot stress that enough. If they're near you, they will come out faster because so much time is spent just walking around. All right, next up is respond to customers' pool. And so what that means in the workplace is demand, of how much your customer wants for the demand. In an FRC sense, we're saying, I need to cut 4 of these drive rails by Tuesday. All right, so I need to figure out how quickly I need to make these 4 drive rails in order to make that deadline of Tuesday. And that's some math, you figured out how long your cycle time is. You're saying it's 10 minutes plus your 5 minutes of working around. It's 15, you divide that by 4, and that's something called tack time. That's how often you need to make a part in order to meet your demand. And then last up in lean manufacturing is pursuing perfection. This is the most overlooked part, but almost the most important. It's really iteration. It's when you see something that's just not working, something that you changed up, you go back, you pursue perfection, you redo the process, you figure out a way to make it better and better. That's really how you get manufacturing success. Is if something's not working or something can be done better, you go back to it. Next up is a 5S. 5S is a process called 5S because there's 5 S's. I know that was a really run-on sentence, but it's a process we go through when we're organizing a shop. I've done this with multiple FRC shops at this point, and school shops and everything like that. But you basically go through a process of sorting things out, setting things in order, shining it up, standardizing, and sustaining. So I'm going to go through an example with my desk to try to relate it to you guys. So I want to organize my desk. I haven't organized my desk in 5 years. I had to organize it when I started working from home because of COVID. And so let's get into it. So before, this is what my desk looked like. It was kind of all over the place. There's a bunch of folders. I honestly had no idea what was in them. Some of them weren't even mine. I have all these trash bags, all these pens that don't even work, these things that don't even make sense, a coaster, a bottle of Advil for some reason that was expired 4 years ago, and stuff like that. And so now I know, okay, I need to spend time going through the process in order to clean this up. So the first step I had to do was sort through all of my stuff, which is the least fun part. When you do it for an FRC shop, I literally recommend taking everything out of that shop and going through it all, going through every box, every bucket. This process takes, weeks, sometimes months to do, which is why people do it in the off season. But what I did here is I pulled everything out, I put it in a laundry basket, and I red tagged items. And so what red tagging means is I don't need this. Why do I have this? We're going to push this to throw it away. And when I have something small like this is easy. I could put it in a garbage bag when I know I want to throw it away. But when you're at an FRC shop and you have, big tools, you have gears, you have stuff like that, identifying at least an area, or all you have to do is put a red sticky note on it and someone knows that we no longer want this and this is going to go in the trash or to donation or something like that, really speeds up the process. So you're not like, oh, did you want this? Did you not? I don't remember what you said. Grab a thing of sticky notes and just start sticking things you don't want. It's the best way to do it. And if someone needs to double check what you're throwing away, and then they can obviously see what needs to be thrown away. All right, so some of these things I chose to move aside for the next process, like you'll see. All right, next up is the set phase. And so what this is you make everything have a home and an efficient place to grab it, like I mentioned before. In this one, I chose to incorporate this box that I found. So I would know where all my paper clips and binder clips were. They always live here. They're just here all the time. They were all over the drawer previously. I put all my pens in that top drawer because that's where I reach to them most. I put my stapler there, my tape, my expo markers. And what I try to do is not have a lot of things just in the bottom of my drawer. I try to have containers for everything. And so all those expo markers are in that expo box. All those pens are in that pencil case. My G2 0.5 pens, which are the best pens you can buy, are in their box. Stapler, you don't really need a box for it, but having everything set in its place is really, really key. And to be honest, my desk is still very organized because I use this. Next up is shine. So after that, you want to kind of be proud of the workspace, that you just spent a bunch of time reorganizing. So I spent time cleaning my desk and whiteboard with disinfectant because no one wants that corona. And so I cleaned it all up, wiped down everything, because if it's shiny, if it's pretty, then I'm going to personally want to keep it more, a little bit more gorgeous. I want to keep it cleaner because I spent so much time cleaning this up. I want to be proud of it. And so when you go clean your shop and you go organize your shop, I highly encourage to get way more students involved, because the more students involved who have to go through the process of doing 5S and cleaning up your shop, the more students will want to keep it clean because they don't want to go through it again. Next up is standardization. And so I made a fake cleaning schedule. I obviously do this every Thursday, but a schedule really helps. And so I made it that every Thursday I have to clean my desk. I got to wipe down my desk. And realistically, I wipe down my desk every day. At the end of the day, it's kind of in process. I put everything away. I work, do my thing. But having some type of standardization is really key. And so when you think about it in an FRC sense, if you know that your shop gets really, really messy on Tuesday nights, but most of your students leave Tuesday nights, maybe make it a different night that you really set everything to order, set aside 30 minutes and do not flake on it, even if you're, on a time crunch, just to shine things up, put stuff away. When you think about it in machining, for example, something like standardization is your lathe needs to be re-oiled every now and then. And so having that process pinned on a board where everyone can see it and saying, I need to re-oil my lathe this many times, this is the person assigned to it, will just put some accountability to things, because you can clean it up, but if you don't have any accountability, you're not going to maintain. And speaking of maintaining, it's sustain. And so sustaining, I already passed the first Thursday of cleaning. I decided the bottom desk wasn't the best that I could do. So I reiterated it and cleaned it more. I actually found I didn't need like half the stuff I ended up keeping. And so I went through it again. And that's part of the process, is you're constantly redoing it. You're constantly figuring out things you could get rid of or things that you should keep. Okay, next up for organization is something called facility layouts. So to the left is a schematic of what a plane hanger would look like. And what a facility layout is I need this to be here. This is where my workers are. These are where my tools are. This is where the thing I'm working on is. And when you have something like that, you're able to really know where things are. And I'm not saying you should create this for your FRC team at all, but I definitely think if you reorganize your shop, you should draw on a whiteboard where you think your tool chest should go, where you think this should go, and anything like that. And so those right images are some of my favorites. This is tool organization within your facility. So that top image with those red tools, I'd highly recommend for a pit specifically. Everything has a home, everything is in its place. You're not really making room for new tools, which you'll see in a little bit. This is stuff that you're going to constantly have. When you open this drawer up, if anything's missing, you know exactly what's missing. And the reason I like that specifically for the pit is you're trying to grab things so quickly. If you know exactly where they are and where they're supposed to go, you're way less likely to, not throw anything out. The bottom picture, I think, is from Adam Savage's YouTube channel, honestly. So he has all of his, drivers all over the place. He has them pinned in an exact location, easy to reach. And so stuff like that, if you have a little shop that doesn't have a lot of, room and horizontal, you could use your vertical walls and actually put stuff up there. And here you could tell what stuff is missing, where things should go. Obviously, a hammer goes here. Obviously, a wrench goes here. And so taking the time and taking a little bit of the cost into spending your money and where you're going to put things so they're easy to grab will really save you a lot of time and money in the long run. You don't lose parts when you know exactly where they go and where they live. All right, next up, Six Sigma. This is a little bit of an out there thing that's not, always specifically FRC, but I thought I'd mention it. This is a lot of what I do in the workplace. So whenever you make products, there are always variations and differences between them. And so to go back to the L bracket example, I'm making 10 L brackets. Some of them are drilled with a bias to the left. Some of them are drilled with a bias to the right. Even though they're small and minuscule, there's still differences. And if those minuscule parts, those minuscule things are important to you and now you can't use that part, then these are defects that we don't want. These are things that we need to figure out how to control a little better. And so some of these are small, like I said, and if they're too large, your parts won't work. That's where Six Sigma comes in. And so the first question I always get when I say Six Sigma is, why in the hell is it called Six Sigma? Six Sigma is derived from a bell curve in statistics. 1 sigma represents essentially 1 standard deviation away from the average in the middle. The defect rate is said to be extremely low if you exhibit Six Sigma. So that picture to the right, that bell curve, is showing you want to be in the blue area. And then your defects are to the right. You have a really low amount of defects. And how you basically do that is going through that schematic at the top is you define what you want, you measure all the things that you're doing, you analyze them. Oh, these are 0.1 out of spec. This is 0.2 out of spec. You take that, you put it in a chart, you see, oh, wow, I have a lot of parts that are all biased to the right. Why is that? How can I fix that? And you go through that process and you control it and you improve it and you go through it again and again. This is something I think is done a lot in the workplace on big parts. I think the way you can apply it to FRC is if you think a part that you've made multiple times is coming out differently every time, you really need to, I would actually sit there with a caliper and measure which side is it going to, what's the difference, and figure out what that is. At the end of the day, it literally could be you're placing in the part backwards every time. You're placing something different. You're not measuring off the same axis. But taking the time to actually do that will save you time in the end and get you better parts that you don't have to keep throwing out, especially in a world where everything takes so long to order, especially bearings and metal and stuff like that. So next up are Kanban boards. And this is, if you don't take anything from my presentation, this is the one thing I think every single person should implement into their shop. So there's 2 different kinds. There's a Kanban board and then there's visual Kanbans. So a Kanban board is essentially kind of like a to-do list, but it's visual. And so what I would suggest is in your shop, you have an area with a bunch of sticky notes and you create these 4 areas. You have a backlog, a to-do, an ongoing, and done. So if we talk about it with parts, for example, you put stuff in the backlog. When you're ready to do it, you put it in to do, then ongoing when it's in process, and then done. Really easy. You keep track of your parts. It's always staying in the done category. Last up are visual Kanbans, red, yellow, and green. The way I like to do it for FRC is you have bolts. Halfway through your bin of bolts, you put a piece of paper saying, when you hit the piece of paper, we need to order new bolts so we don't constantly need to keep reordering. Last up, I'll go through these pretty quickly. I know I'm running out of time. So timing and scheduling. I know we had a workshop on it a little bit ago, but Gantt charts are really useful. Essentially, you're planning when you need to do things and if they influence something else. Next up is sequencing and scheduling and machine time. This is a little bit more involved and I'm happy to get into it on Discord, but if you have 2 mills, you need to figure out which ones and what time you should make parts so that you're completing parts on time. If you have a really long process mill, then you make that first because it's going to take longer. And then on your other machine, you can use that time up to do other stuff that you want that day. Critical path is essentially kind of like a Gantt chart. You're figuring out when you want stuff done. I like to think of the end of your critical path, that number 11, as bag day. I know bag day doesn't exist anymore, but let's think of it that way. And that red line is, I need to accomplish these at these date or I don't make the date on the 11th. The rest of them are, you can, vary on days. Here's some fun shop organization. All the tools are in one area. This is the Code Orange shop. They have really nice dividers and bins with everything in them and labeled nicely. The bin is labeled and the rail. And then communication and the want to iterate is the last thing in a manufacturing engineer's tool belt. It's the only way to find success in manufacturing, and it's to listen effectively and communicate with your team. You really need to sit down and ask the team and yourself what's working, what isn't, what are your bottlenecks, where can you improve? And these discussions need to be constant. I used to take it really personally when stuff would not work that I put the time into, but at the end of the day, you can't take it personally. You just got to make it better so your shop is more successful and your manufacturing is more successful. So with that, are there any questions? I know I ran a little over. Yep.
No, you're good on time. There
Ah,
are a few questions that I've got
go
here.
for it.
So I'm just going to start from the beginning again. And
Okay.
so if teams do not have access to machines such as CNC machines, mills, lathes, or more powerful machines that usually teams with more money have, what would you recommend some other methods for them to achieve a similar quality or be on par with these better teams?
Awesome question. I think how you can achieve similar quality and accuracy when you don't have necessarily the machines perfect for the job is you have to spend time. As cheesy as it sounds, you got to measure 4 times and cut once. If you know that your part needs to be super accurate, you need to spend the time early on and really make that part exactly where you need to cut it so the instructions are clear, so it's right there. I truly believe you can build an award-winning Einstein robot with power tools and hand tools. I don't think you always need a mill. I don't think you always need a lathe. I think you can build it with just that stuff, and people have been on Einstein with it. What I would spend the time doing if you are that team is spend the time really understanding that tool, spend the time building up some of the tooling you could use to make it more accurate. So if you have something like a drill press, you could use it to cut accurate holes similar to a mill if you just spend the time creating some tooling and fixturing to hold parts really well. Because typically on drill press, you're just, put in some vice grips and drilling something. But if you spend the time creating a fixture, you're going to make accurate parts. Spend the time on the tooling, way less money, way less energy than buying a mill and CNCs and stuff like that.
All right, and I guess following up on that, speaking of off season, getting ready with all these tooling and jigs and stuff, is there anything that you recommend teams to present to new members or to members who haven't had much experience on these machines to work on during the off season so they can get familiar and spend the time to know how to really use the right tools?
Awesome. So if it wasn't COVID, what I would say is that 3476 training is really great. It links to a bunch of videos on how to use specific tools. And I would spend the time watching that and making sure you understand that. And then if it wasn't COVID, you go in person and practice those skills. You give them a little project of this is how you build this thing. I want you to do it in front of me. Have them measured at the end so they know if they're actually hitting accuracy. Then they learn how to measure. They learn that, oh, you need to change this up to be more accurate. In COVID times, my strongest recommendation is to watch those videos, to watch training videos, and try to get as familiar as possible. It's never going to be like working with your hands, but at least getting them engaged and having an open forum where they can ask questions on how would I make this? How would I make that? And if you really want to go a little bit more in depth, you can cat apart and ask them, how would you make this? I tell them to go through all the tools in their little toolkit. How would you make this part? That's what we did in college for manufacturing engineering. Our professor would give us a part and be like, hey, how do you make it? We didn't build it. We just wrote it on a piece of paper. This is how I'd make it. And that's a good place to start.
All right, sounds good. And next, so during time crunch periods, right before bag day, obviously back when there was still bag day, would you value accuracy and precision or getting something done quickly and on time?
So that goes back to the value added. And so that's really up to your team. If your utmost goal is to finish your robot on time, which is the utmost goal for most teams, you put that over everything. And so if that means a slip in accuracy, that means a slip in accuracy. But the reason we use all these different scheduling things is so that slip doesn't always need to happen. So if you know that I need to accomplish something at this time, then you're more likely to get that accuracy than if you're just like, I need to complete it week 2. Yeah, week 2. But if you set the date and you hold yourself strict to the date, you're able to achieve that accuracy. But at the end of it, this is a robot. You need a robot that works. If it's the final time and you need something done, you're going to try to be as accurate as possible. You get that robot together. And if you need to make a part again later for when you're at competition and can put it on, you make that part and you put it on if it's necessary.
Okay, and then moving on to more of your organizational methods. For implementing all of these methods to either keep the shop organized or the design process organized, where's a good place to start for teams that currently don't have these processes in place? Where's a good place to, I guess, just break the ice into changing their current organizational methods or formatting and I guess how the team runs?
I think starting small is the best thing you could do when it's seemingly overwhelming to, organize something so big and so grand. I know I've been definitely overwhelmed. And so what I would suggest is if you want to implement this process and you want to get a little bit more organized, start off with your tool chest. Literally just go through your tool chest. There's so much crap in there probably. Go through it, figure out which tools you need, figure out where to set them into place. It's easy. You can kind of get kids involved and figure it out that way. And then you can move on to bigger things, but at least you'll get, your foot in the water before you have to tackle this huge thing.
Right. And the same goes for design, timeline, design process, organization.
Yeah.
Where would you start with that? Because it's really hard to just implement a whole new system that the team is completely unfamiliar with. So how would you go about doing that?
Yeah. So for design like CAD and doing stuff like that, like
Yeah,
organizing
referring
that.
back to your Six Sigma,
Okay.
5S, all of that.
So for that sense, I would give the same advice. I would start small. If there's something that you can do to, let's say you want to lay out your facility, or if you want to make parts in a fixture, anything like that. If you start off small and do one thing at a time, it's easier to get kids on board because it's not this like whole new process thrown at them. So if your process already is, we're going to put this drawing in this pan and give it to you, and that's how you make the part. Okay, instead of that, let's put this drawing in a pan, give it to you, and then put a sticky note on our Kanban board and then move it over when you're done. It's like that little addition so it doesn't overwhelm, but it can do a lot. And so when you start adding these in, it'll start flowing and making sense to the students.
Okay, really awesome. Thank you so much for your amazing presentation. I know I really enjoyed it. I love to hear the passion in your voice about it. And
Aw.
we're going to move on to trivia night, which is the next in our schedule.